An end-use part is any tangible good that is sold as product, used as a subassembly, or as a component in a product. But they may not be sold at all. End-use parts are also placed in service within the company's own operations. For example, a component used on its packaging equipment. Almost all industries from consumer electronics to aerospace and military sell end-use parts, and they come in all shapes, sizes, and materials from plastics to metals. For those plastic parts, FDM is an alternative for pilot runs to full-scale end-use part production. FDM offers a more flexible and inventory-friendly manufacturing solution that is fast, cost-effective, and efficient. Traditionally, parts are manufactured using processes such as molding, casting, and machining. For each of these processes, the primary focus is on how to design for capability, optimization, and efficiency. Because of this, once the process has been developed, it is static, and with any change, cost rises, throughput drops, and manufacturing efficiency tumbles. With FDM, this is not the case. FDM allows for optimization of part design for function and a dynamic production environment that not only allows but encourages continuous improvements and design modifications. This flexibility enables companies to expand their product lines and markets served with solution-based selling. Affordable and efficient low-volume manufacturing becomes practical. FDM is a best fit when production volumes are anywhere from a quantity of 1 to 1,000, and the designs are moderately to very complex. An order quantity of 1 usually means customized products. Industries such as medical or motorsports are two examples where customized products are commonplace. In the medical field, FDM is used for things like prosthetics and surgical guides. In motorsports, manifolds, instrument pods, and hood vents often rely on FDM. Aerospace is an example of low-volume, high-value production, which is ideal for FDM. FDM is used for end-use parts throughout the entire product life cycle. During the alpha and beta phases of product release, it can be used to make parts for pilot production runs. Some will use a raw FDM part. Others will use secondary operations such as sanding, filing, or automated processes to get production-ready parts. Once the product has been validated and all component designs are frozen, FDM can be used as a bridge to production, making end-use parts while waiting for delivery of tooling and manufacturing equipment. For some of the more complicated geometries and customizable solutions, full production with FDM is the practical option. Since traditional tooling is aimed at production of a single design, FDM is an efficient and optimized solution for products that are continuously changing, either through product revisions or through order-by-order customization for products such as prosthetics. When a product approaches the end of its life, companies once again turn to FDM. As orders decline and tooling requires replacement, FDM is an alternative that extends the product's life with minimal expense and little or no inventory to carry. In this phase, or after a product has been retired, FDM can also continue to manufacture spare parts as they are requested. So what qualifies a part as a good candidate for FDM end use? 1. The design is expected to change frequently. 2. The part is a one-off. Look for the customized product or the solutions-based products that are encountered in motorsports and processing equipment, for example. 3. Production costs can be decreased by consolidating parts so that there are less components to assemble and manufacture. 4. The product demands or deserves a design that is impossible or impractical to manufacture with traditional methods. Companies that are open to change and innovation, open to non-traditional manufacturing approaches, are also open to making adjustments to the traditional design process to fully capitalize on all the benefits FDM has to offer. For further information, contact Stratasys Application Support.
This is just a quantum leap forward.
It allows us to take what's on the computer screen and turn it into a real-life physical model in a matter of hours.
There is very much a wow factor.
Really changes the way we think about production.
This is one of those industries that matches perfectly with 3D printing, additive manufacturing, because we need custom everything.
The client can come in and see that we're not just one of 8,000 processors, that we actually invested in technology that makes them better, differentiates us from everyone else.
Now we've got a 3D Fenway Park. This came off a printer? Is that what you're telling me? Believe it or not, it's a 3D printer that jets a resin that turns into a plastic when it's done.
By having this 3D printer, we can have a very, very short turnaround time, more than any other company in this field.
You can rapidly prototype complex products without the need for the major capital investment in a production line.
The technology affords you the ability to actually get back one resource in this world you can't buy in its time.
It allows our students a lot more hands-on opportunities. They can take the object and they can test it and they can see the theory being supported by the actual physical results. You know, that type of information is priceless. You guys are really on the cutting edge.
They can take it into the big boss at the company. Here you go, boss. We've got a great new system. We're going to sell 1 million of them.
There's really no words for me to describe how cool it is.
Stratasys is able to take a CAD file, we can import it into the machine and print a part in hours.
You can redesign the part to take advantage of what 3D printing can really do, which is very complex geometries that just can't be made by any other means.
We're working with Stratasys. What we're trying to do is take their technology and go from prototyping to real manufacturing. You can make parts, you can make systems that can't be made any other way.
Having this technology here was a game changer. It was the difference between killing a program and keeping it moving forward.
Injection molding is one of the most widely used manufacturing processes because it is ideal for high-volume manufacturing. Although additive manufacturing makes form and fit prototypes of injection molded parts, it cannot deliver the functional performance of production materials. To fill this void, PolyJet offers 3D printed injection molds without the hassle, time, and cost of machine soft tooling.
Für die Herstellung dieses Großserienwerkzeuges benötigen wir 8 Wochen Zeit und so ein Werkzeug kostet ca. 40.000 €. Diese gedruckten Werkzeugeinsätze liegen in der Preisklasse von 1.000 € und sind innerhalb von einem Tag herstellbar.
Replace your machined prototype tooling with PolyJet injection molds for real parts in real materials in just days. At just 1/3 to 1/2 the cost, PolyJet makes it convenient and affordable to qualify your products before committing to production molds. Visit Stratasys.com to discover how and to find your local reseller.
Fused Deposition Modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual-heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical. PolyJet is a layer additive manufacturing technology used to develop plastic prototypes from 3D CAD data. This rapid prototyping process uses inkjet technology combined with UV curable materials to quickly and economically produce highly detailed and accurate physical prototypes. PolyJet is one of the fastest prototyping processes available to develop high-precision physical parts and is ideal for smaller parts, appearance models, and master patterns. The PolyJet process begins by slicing CAD data into cross-sections or layers as thin as 6/10,000ths of an inch. The data is then transferred to the PolyJet machine, which begins constructing the object one layer at a time. Similar to how an inkjet printer lays down pigment, the PolyJet printhead deposits small amounts of ultraviolet curable material on the build platform, eventually forming a single cross-section of the part. An ultraviolet light attached to the printhead simultaneously cures the material as it is printed. Once a cross-section is complete, the build platform is lowered slightly to make room for the next layer. As the part is built, support material is added to give supplemental strength to fine structures and down-facing surfaces. After all of the layers have been created, the finished part is removed from the platform and cleaned. Although finishing is not necessary, a number of hand sanding and paint options are available through service providers such as Solid Concepts. PolyJet parts are well suited for quick, economical prototypes requiring exceptional detail, surface finish, and edge visualization. PolyJet is ideal for a wide range of industries, including medical, entertainment, consumer products, automotive, and industrial design.
Manufacturing relies on jigs and fixtures to maintain high levels of quality and production efficiency. Time is money, and money is money too. With FDM jigs and fixtures, you can save both. FDM works great for complex and organic designs, and it can perform as well or better than your traditional jigs and fixtures.
Here at Oric Manufacturing, we're able to use FDM and rapid prototyping to create jigs and fixtures because it's faster than doing things like CNC machining, and it's lighter and it's cheaper than any other process that we've used.
FDM jigs and fixtures can reduce lead times up to 90% and provide cost reductions of up to 95%. Streamline your process, save time, save money. Try FDM jigs and fixtures at your facility. Visit Stratasys.com to find your local reseller and find out how much you can save.
Oric manufactures the best vacuum cleaners in the world. We're the only manufacturer of vacuum cleaners in the United States, and we make the lightest weight, most powerful, simplest vacuum cleaners available. Stratasys systems here at Oric have helped improve our new product development and even some of our sustaining product capabilities.
One of the things we can do here is we do not have to do drafting and some of the radiuses and things, the sharp corners that we might do in a new design. So we're able to create new parts very quickly and can test those parts from a design side.
I
use FDM here to build fixtures to measure our parts for our uprights and floor care products on the coordinate measuring machine. With traditional measuring methods, a lot of times we couldn't do any programming for the CMM to do first article inspection until the parts are actually made in the new mold. That could lead up to well over a month of bottleneck. Everybody just waiting on first article inspections. Now with FDM, we can make the fixtures, we can make prototypes of the actual parts before the molds are even made. And then when the parts come in the door from the actual mold, I'm ready to go. All I gotta do is bolt the fixture on, put the part on, press the go button on the CMM, and I can knock all the parts down to maybe 2 days.
Beyond new product development, we also use rapid prototyping to be able to help place our products for assembly. Assembly on carts, things like that. It provides the capability for our assemblers not to have 5 hands to be able to put parts together.
Using the Stratasys system helps us in a lot of ways. A lot of these nests have some complex shapes to them, and typically if you were to ask a machinist to machine one of these out, he could easily spend a day on each one of these nests. Where with the Stratasys system, we can turn out multiple of these in the course of the day.
If you're considering using the Fortis for manufacturing, I would highly recommend it because it's beneficial in a high-paced, fast-moving environment.
FDM uses go well beyond the new product development stage. Assembly, manufacturing, quality control, that type of stuff is better, cheaper, and easier to manufacture, quicker than any other process that we've used.
Wherever there is a need to hold, position, place, or organize, you will find jigs and fixtures. They are used by nearly all industries: aerospace, automotive, consumer products, medical devices, and healthcare, just to name a few. Within a company, you will find them in research and development, manufacturing and assembly, inventory control, quality control, and transportation. We'll walk you through a few of those departments. Tools that once were traditionally fabricated out of wood, plastic, and metal, either with hand tools or machine tools, are being made with FDM. By simply substituting FDM for traditional processes, companies are producing jigs and fixtures faster and at a lower cost, and they're making far more of them because of the ease and efficiency. Before launching a new product, extensive research, development, and testing are performed, and FDM jigs and fixtures are there to help. From fluid line mounting fixtures to gauge mounting fixtures, check gauges, and fan testing rigs. Need to test a light bulb or specialized hardware? FDM can make a fixture for that too. The durable FDM plastics are perfect for your life cycle testing. Fans, keypads, vacuum cleaners, and many other products. When testing reveals a need for a change, simply 3D print another FDM jig or fixture for the next go-around. On the production floor, FDM jigs and fixtures make work easier and safer. And companies that use FDM find that they have more of them than ever, since they are so easy and inexpensive. Sandcasting is a simple, cost-effective approach for manufacturing metal parts that are used in many industries, such as industrial equipment, aerospace, automotive, defense, agricultural equipment, and consumer products. To make the sand molds for casting metal parts, foundries use loose patterns, split patterns, and match plates. They also need patterns for gate and runner systems and sand molding tools called core boxes. FDM manufactures these mold-making items. Even before the foundry starts making sandcasting molds, it may benefit from using FDM to make models, prototypes, and sales samples of the castings to validate product designs and get customer approval to proceed with the order. With that approval, the sandcasting process begins, and it starts with a pattern production. Traditionally, skilled pattern makers in woodworking or metal shops created sandcasting patterns. As the availability of pattern shops has declined, innovative and efficient options such as FDM have filled the void. Complex patterns that once took several weeks to make are now produced in-house in only a few hours on an FDM system. Gates and runners feed molten metal to the part cavities in a sandcasting mold, but getting the mold to fill properly often means adjustments. Making an interchangeable FDM gate and runner system gives the foundry the means to do test pours, redesign the gates and runners, and quickly rebuild them. From prototypes to production orders, FDM is an ideal tool for making castings for low-volume aerospace parts or mass-produced hardware for doors and windows. Once the FDM patterns, gates, and runners are made, the balance of the sandcasting process is unchanged. First, the FDM patterns are sanded. Next, an optional foundry coat is applied. This seals the pattern and improves abrasion resistance. Now, the pattern is bolted to the match plate blank, and the gates and runners are attached. Then, a mold release is applied. With FDM's real thermoplastics, the patterns are robust enough to withstand the sand abrasion and the compaction pressures when forming the sand molds for any of the methods. Loose pattern sandcasting with hand ramming forces for no-bake sandcasting, and match plate inserts for green sandcasting. Once the sand has been formed around the pattern to create a cope and drag, the sand molds are ready for metal casting. Molten metal is poured into the sand mold. After cooling, the sand is removed with vibratory machines or through hand processes. Sandblasting may be used to remove any residual sand trapped in the cast metal surface. The raw metal castings then go through secondary processes, including gate and runner removal, drilling, sanding, and machining. These secondary processes can also benefit from FDM. Guides for core setting and complex assemblies, drill bushing fixtures for faster machining, jigs and fixtures for straightening and inspecting finished part dimensions. From pattern to finished metal casting, FDM makes the process fast, accurate, and reliable. For further information, contact Stratasys Application Support. Blow molding excels at what most other processes cannot do. Hollow, thin-walled products, such as beverage bottles, made in the millions. But what do you do when you need a few or a few thousand for evaluation or customer orders? The answer: 3D print your blow molds with PolyJet. In just a few hours, you can be molding clear, translucent, or opaque parts in production-grade materials like polyethylene, polypropylene, and PET. With PolyJet, you have a fast and affordable way to make products with the appearance and function of blow-molded parts from a production run. With time and cost savings of 75 to 95%, there is no reason to launch from design models straight to production tooling. Use PolyJet to 3D print your blow molds and then proceed to production with confidence. Visit Stratasys.com to find your local reseller and discover all the advantages.